Hello and welcome back to the lab. Today on the bench we have a 7904A. This is the fastest of the 7K frames that actually I own, and probably where I'm going to top the line out for me personally. They do make one faster than this. They make a 1 gigahertz frame, which is the 7104. I've done a lot of digging into the 7104, and the reason I'm probably not going to pick one up is because to get the brightness on the screen for the 1 gig, they used a microchannel plate CRT. And while it worked incredibly well for the time, and it was a fantastic piece of equipment, and everything was good with it, they aren't aging well. It's very hard to keep burning off the screen. The screens are eating themselves to get the brightness, and the tubes aren't being made anymore, so they're just aging out. So I'll probably top it here. For 1 gig, I have the DSA 602. Now I am also going to need to push the lab faster than that, probably in like the 6 gig range. Not sure yet exactly how I'm going to pull that one off, but I've had the lab warming up for a little while. Actually, is my nope, not quite warmed up yet. So I want to do a calibration on this today and get it up and ready to go. I'm also going to do an LED mod to this. I will leave some links in the description below once I have them from the gentleman that made this board, which is the LED driver board. And we have a schematic. Turns out, unlike the 7603, because of the way the readout or the illumination works, because of the photos and things like that, it has a pulsed illumination where when it sweeps it illuminates, but then it doesn't. Doing an LED mod on a 7904A is not as straightforward as doing it on a 7603. So we needed an LED driver board, and there is some modifications we need to do to the scope, so we'll do that as we're going through. While the lab's warming up, we'll put the LEDs in, then we'll give this frame a cal, because I have some 7K plugins that I'd like to get calibrated and back to working, but my calibration scope, which was my 7704, is actually over at the office and isn't here. So I need a 4-bay frame, better than 200 megahertz, that I can do the calibrations on. Hence this guy. Here is the LED interface board. Couple of NPN and PNP transistors to do the driving, and it just sits on the positive 15 volt rail. To get this installed in the scope, this sits in between the A1 board and the power supply. So this tail will plug into the power supply. This will take the A1 plug out from the power supply and bring it to the A1 board. And then we have to remove R301 from the A1 front panel board to get this to work. I have been told that is an incredibly critical step, and if you don't do that, bad things happen. So we will get that done. I was also sent some wide-angle white high-brightness LEDs along with the board, and it will be we need to convert the LEDs from a parallel string to a series string. So the good news is that's not too difficult. We'll just get that done, and then we will be able to move forward. So I'm going to get the scope open, and I will show you guys where this gets installed. Okay, well, R301 was fun to find. This is our resistor right here that needs to come out, but it's the only 300 part on this board. The rest of this board is 1900, so we have one part here instead of being down below, but I need to remove that resistor to get started. Okay, and after a bit of soldering work, we have turned a parallel string into a series string. I had to cut the traces in a few places. I had to put this jumper wire in, but we have a series LED set. So now I just got to get it in the scope. Okay, I've triple checked the wiring. Let's put power to it and see what happens. No smoke. Dirty potentiometer. However, we have Graticule lights. Very nice. Ugh, I have to clean up that control. Like, that control's horrendous. But that's why we're in here. So, all right, let me get everything put back together, and then I'll work on cleaning that control. Okay, here's the interface board mounted at the hole. This hole's existing in the chassis, so nothing even needed to be drilled. All you need is a bolt, a washer, and a screw, or a nut, and board sits in. We do the modification. The longest part about that whole process was turning the LEDs into a series set. So everything's good. I'm going to lay the unit on its side now and go after those controls because they need to be cleaned. But and then give it some time to dry out, and we'll do a calibration on it. Make sure it works. Okay, here's a bit about what we're up against. I've got the controls. They're just cleaning out right now, so I can take a look at a little bit of other places in the scope, see what we're going to get into with adjustments. So we have some controls here, 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 and here, but then we have the structure right here that's part of the high-speed network with these ceramic ICs. So I'm going to have to be super careful during the calibration not to disturb this high-speed network, like move the resistors around, things like that. I don't want to bend any of this because I don't want to change its response. We'll probably have to tune this coil. We have the deflection plates coming in. This is the vertical, horizontals over here. So this is the high speed, but it even leaves on... this is probably actually transmission line into the CRT, so we have a lot of high-speed, very fragile stuff in here. The service manual even calls out using a non-conductive tool, so none of this gets shorted out and these ICs get blown up. There's a lot of unobtainium in here. If I run into a problem, I will not be able to get any more of these hybrids. There's another one down here for the Z-axis over that way, which we'll get to. The horizontal doesn't have any of the super fast stuff. So I'm gonna have to be very gentle while we're working in these areas to make sure nothing happens to these hybrids while we're calibrating. Well, it's amazing what a little bit of switch cleaning will do. On the controls. And with the add-in board, if I set this over to pulsed and I manually pulse it, the pulsed functionality is preserved. So that is one of the things that I was hoping would stick around. Oh well, that is one of the things that was designed to be preserved with this. Why you need the add-in board as opposed to just putting the LEDs in, because just putting the LEDs in messes with the pulsed and gated illumination. So I've had most of the lab warming up now for about an hour and a half, 2 hours. I need to pull a service manual for the unit, and then we will go through the calibration on the frame. I won't be doing any of the calibrations of the plugins on this video, because to do a full calibration on one of these 7K frames, you have to calibrate the frame, then you have to calibrate the vertical, then you have to calibrate the time base, and that's 3 different calibrations and alignments. So this video will be just on the frame itself, which is primarily power supply. To put it into the 400 series terms that I used when I did the 400 series, or the 465 calibration, it would be the power supply of the tube. I get a lot of questions, and I see a lot of questions about these calibration fixtures and signal standardizers. The answer to the question of, do you need one of these to calibrate the scope? No. A scope cal can be done with a vertical amplifier and a time base. So what you lose is the normalization between the two bays. So if you calibrate it with a vertical plug-in, you're not guaranteed that the scope will still be in spec if you pull this out and move it into the other bay. So you can calibrate it that way. However, the calibration can be thrown off given the response of the individual bays. So that's what the standardization fixtures do. They allow matching between the bays so you can move plugins in and out and things like that, and the scope still be in spec. Now on these particular calibrators, I don't know if it's going to need the -01 or if it's going to need the -2 or the -1. The only difference between these two calibration fixtures is the speed of the fixture. The -2 is rated for the 1 gigahertz scope. I think you can use a -1 for the 500 and below. There's a third one that I don't have, which is a -0, which is slower than the -1. So you can use a -1 for every scope below, like a -1 is for a 7854 and below, so the 400 megahertz and below. I know for a fact the -1 is able to be used. I don't know if the -1 can be used for the 7904. The -2, however, is necessary for the 7104. This one's actually a lot more rare. There's a lot of -1s floating around and some -0s. The -2s are a lot more rare. Inside the -2, we have some ceramic hybrids. These actually match the hybrids that are in the 7904A and the 7104. They're the same chips. But then this switch bank right here, this is the elastomer switch bank. It is very critical that this doesn't get disassembled. There was special alignment jigs when they put this together for aligning up these switches and things like that. These are, if you take the wrong screws out and you take the whole switch contact apart, they it is incredibly difficult, if not impossible, to get it realigned. So be very careful. Do not take this apart unless absolutely necessary. And they use the elastomer for the high frequency because this is rated up to a gigahertz for the 7104. The -2 calibration unit has the standard tech reed switches that are everywhere, or the finger switches that are everywhere, so it's easier. The -2s are much easier to work on, or the -1s are much easier to work on than the -2s, but I will check the documentation to figure out which one we need while the scope warms up. Well, it turns out the calibration document says I can use either the -1 or -2 signal standardizers. However, it calls out I need 2 of them, which is kind of nuts. But I also found out I'm not going to be able to do the calibration on this at the moment because I need a fully functioning SG504, which I don't have. The SG504 that I do have is kind of broke. So I'm going to put the covers back on this, work on that video. Everyone will see this video after the SG504 because I need to get the high series of the SG504 working because I do need the leveled sine wave up to a gigahertz. Okay, we are back in the lab and I got the SG503 fixed. That was fun, as everyone saw in the previous video. So I am back to working on the 7904A. I got a service document up. I've got adjustment locations. Vertical mode left. Trace separation mid-range. A source. Vert mode. Fully counterclockwise on the A and B trace. Focus is mid-range. Fully counterclockwise. Control illumination is medium. So we'll need to be on this side of the scope first. So I'll move it, and then we'll do some adjustments. Okay, chassis ground's up here. And of course, our pre-regulator test point would be in the bottom of the power supply, because why wouldn't it be anywhere else? Spec wants 108 volts. I'm at 107.79. We can tweak it a little bit, but I'm actually thinking I'm going to leave it alone because this is pre-regulation. So this is pre-regulation. We're at we're at 107.79. However, we're at 118 volts line voltage tonight. So where I'm at, we can sometimes run up to 123, 124. So 118 is pretty low. It's pretty cold outside, so a lot of people have heaters running, so the line voltage is sagging a little bit tonight. So I'm not going to mess with the pre-regulator. Everything's fine. We're within spec because my spec is 107.5 to 108.5, so I'm going to leave that one well enough alone. Okay, to service the power supply, you have to remove the power unit out of the back of the scope. My heatsink is kind of warm, but it is warm down here. Ground is here, and then we have our test points here. Now, this is a non-insulated tool where I'm pointing. I'm going to be extremely careful when working around this. There's line voltages, currents, bulk capacitors down in the bottom of this thing. Extreme care has to be taken when servicing anything, really, but especially a scope like this that has elevated voltages, line voltages, high currents all over the place. I mean, I got a couple of kV up in here, so take care if you're following along. Obviously, you are doing so at your own risk. But always use caution when servicing live equipment. Actually, I'm going to switch out probes. That went, no. I will still use, I'm going to use this mini grabber probe to keep my hands nice away from the test points while I am testing them. All right, here's our plus 50 test setup. The manual says negative 50, but it should be plus 50. I don't have a negative 50 volt test point on this board, so it is plus 50. So that is there are our test points, and we have 49.97, so regulation looks okay so far. The service manual does not call out the ripple check step. I'm just going to do that just to for completeness sake, and to make sure the power supply doesn't have excess. It'll give me an indication of if I need to work on capacitors or anything like that. One thing to note with these power supplies is the 4-bay frames are a switching supply. The 3-bay frames are usually a linear supply, so they're different. Okay, checking the ripple on the 14 volt test point, plus 15 volts. It's running a little high. Let me check the others. The ripple on the negative 15 volt rail is the same, right around 10 millivolts, so I'll keep going. The ripple on the plus 50 volt rail is about 0.8, so it's a lot better for being a 50 volt rail. All right, we'll check the ripple on the 5 volt rail. $7 millivolts. 8. And we'll check the ripple on a negative 50 volt rail. Eight as well. So looks like the power supply is consistent. So I'm going to leave it and we'll see how the calibration goes. Or I'm actually going to check the documentation and see if there is a ripple spec. There may or may not be. And then we'll go from there. Okay, I got to put the scope back together because the calibration or the service manual did not call out a ripple spec on the power supply. So we're going to run with it and see what it goes, see how it goes. The scope is also not drawing excessive current, so we should be all right. So I'm going to button this back up, make this a little bit safer to work on, and be back. It also should be noted when handling and moving around the power supply, the unit is off and unplugged. Okay, we're into the really spicy voltages. This is the high voltage section. Where's my pointer? I'm not even going to do this with my finger. The test point is right here underneath this transistor. I'm picking up ground right here. I need 96 to 100 volts on this test point, and I am actually off. We have 89. So we will do an adjustment of the spicy voltages. Well, that pot, when it finally broke loose, wanted to move like crazy. Our target is 100 volts, so I am going to set the meter to a kV range so we don't have a switching problem right at 100 volts. And I'm going to like that right there. The potentiometer in question was this one right here. The tuning tool I'm using is a insulated, it does have a steel tip, but these only go in about a ½ an inch into the shaft of the tuning tool. So I have an insulated tuning tool, and doing that with one hand, not even touching the bench with the other hand, just to make sure nothing gets jumpy when the high voltage supply is open. What I got to do now is I have to button the high voltage supply back up. To get the cover off the high voltage supply, it's a screw here, and screw here, and then it slides this way into the case and comes out. To put it back together, it's the reverse. It slides in. The scope is off when you're doing this. And then we run the screws in with my overly long proboscis screwdriver. One thing to note when putting machine screws back in, don't overly tighten everything, or don't tighten things as you go. Put everything in quasi-loose, because it allows the stuff to kind of float around when all the screws get lined back up, and then snug everything up. After it's assembled. All right, turn the scope back on so it doesn't cool off too much. That's always fun. Oops. We'll be careful. Moving to the right of the fan, we have a Z-axis board. This is what the next adjustments are going to be. All right, here's our test point with the 10x scope probe hooked up. I'll move over to the Rigel, and let's see, what's our adjustment? Because it's slightly out. Not much, but slightly. This right here is going to be R135. It's going to be our adjustment point. I have the Rigel in a bad spot. The glare is kind of bad. Channel 1's at ground. At ground level is the very bottom of the Graticule. We're at 2 volts per division. And we should have a stable waveform at 10 volts. We're at 10.2, so I need to come down about 200 millivolts. With this minimum value is the important one. So we will come down and what's weird is right is down. I had it for a second. I'm going to switch over to a metal screwdriver because there's a lot of lash in this control. There we go. Perfect. All right, so now we wind up the intensity all the way. So we're looking for a peak-to-peak waveform of 63 volts. We're at 68, so we're a little hot. So we got to bring that down a bit to 63, and then we have to check both, and then we have to dance back and forth on these until they are both at 10 and 63. Go. All right, let's turn it all the way back down. Check our baseline. We're at 10.4. All the way up. Give it a little more. I'd say this probably has the factory calibration on it, because that's close enough where with a with the equipment of the day, that's probably where it fell out. So this is very, very close in spec. I'm not having to do many adjustments, so that's turning out nice. One thing also to note when using this document, it tells you amplifier and time base, and these move for setup, and this is kind of your scope setup parameters. It doesn't say that. It's not written out like the other service manuals that I'm used to, so pay attention to the pictures. Okay, I have everything all set up to adjust the Z-axis transient response, which is going to be C180, C150, C155, R150, and R155. Here's C180, R150, C150, C155, R155, and our test point is 183. But if we take a look at our test point, you can see the end of the probe here coming out of the board. We have some fantastic high frequency probing built into the board. So if you take a look here, actually let me move the cable out of the way. The scope is on, so I need to be careful where I touch and put wires. But if you take a look right here, you'll see this socket with the tip in the middle. If you take the hook off of the scope probe, you have the signal tip plus the ground shield all the way up for high frequency. So you take the scope probe and you just shove it into the connector, and that gives you a very good high frequency connection, not using the long ground lead as a antenna pickup. So this looks okay, but it is out of adjustment. So I'll move over to the scope and we'll take a look at that. So what I'm looking at is this corner right here. This is a little peaked up, so I need to tamp this down a little bit. So we want this to be a nice straight edge as fast as possible, so we don't want it to roll up, because if it's rolling up, that's too slow. So you want it to bounce up, but then you want these aberrations at the very front corner to be less. So I'll focus in on the amp while I'm doing the adjustment, and then I will focus back in on the scope. Well, in looking at this with a faster scope, we have a nice sharp edge, so we're going to leave that alone. Looks like we do not need to adjust the Z-axis transient response because everything is looking good. This stacked up a little bit on the 100 megahertz scope and made it look a little taller than it was, so I needed to get a faster scope. I've got this into a 7A26 with a 200 megahertz probe on a 200 megahertz plug-in on a 400 megahertz frame. So that one's looking good. All right, after you check the high amplitude, it wants you to roll it down to 1.5 divisions, and then it wants to look, and then the service manual wants us to look for the front aberrations for 0.75 divisions. This is just fine, so we don't need to adjust anything. Okay, we're checking focus, test point 83, and ground is on the chassis. We're looking for a reading between 120 and 120 and 126 volts. I'm at 123, so that is perfect and does not need to be adjusted. This is turning out to be in very good condition for its age. Calibration-wise, there's not much to do. Okay, here's the front end setup for B6. We're looking at the B contrast, and if I turn this through its entire range, we get very bright, dimmer, but still bright. So it wants a well-defined display. I'm going to go right there because I could even probably back this off. Yeah, I can almost make that disappear and still have the B contrast. So right about there is probably good for me. All right, now I need to get some signal standardizers out because I need standardizer time base, standardizer time base. Okay, to do the grid bias, time bases are out, standardizers are in. Chassis ground, TP 183, and we're back to the DMM. Okay, to make this measurement a little easier, we're actually going to have a play around with the meter. So what we're going to do is we're going to turn on relative measurement. And now, when that says 3.6 to 4.4, we should just be able to see a spot. Oh no, the grid bias is way off. R65, located on the high voltage board. Okay. R65 is this bottom control right here. This is what I have to adjust, but I have to see the front of the tube. You bring it up so you can see the spot, and then you turn it you bring it up so you can see the spot, and then you just turn it so the spot disappears. I usually do this lights down for this because it makes it easier to see. But, and this is on the high voltage board, so definitely take care. Oh, wow. Got really bright. Okay, so we see our spot. Let me move. Can I? Yeah, I can. No, I can't move its position off the center line. I was going to try to get it out of the way of the Graticule, but that's not going to happen. I could still see it. The camera can't, but I can still see it just a touch. And now it's gone. There we go. Apologize for the bad angles, but I've got everything set up now. Left A, step response, 1 megahertz rep rate, 10 nanoseconds per division. You crank this all the way up like so. Now I need to set the focus, which is R63 for the best focus, and then I need to make sure it's more positive than -12. It is very much more positive than -12. Okay, here's the test setup for part 10. We're about to check the external Z reference. So I've got everything set up. I need to get a BNC-T on here. I take this, run this around to the back of the scope to Z in. Okay, got Z axis input hooked up. It's the very bottom BNC on the back of the scope. And the top half disappeared. Bottom half is intensified. That's exactly what we expect. So the Z-axis input is working. Okay, gonna have to work on the calibrator. Don't I have to pull a transistor for this? Okay, to make it easy, you don't have to get under here. You have to get under here. The adjustment points for the 0.4 volts and the 1 kilohertz are on the bottom of the plug-in bay, and that's where you can get to them. The Rigol says I'm at 0.4 exactly, and the frequency counter says I'm at 1.008 kilohertz, so we're off by 8 hertz. If I turn it any more, the pot's going to fall to like 950, so I'm going to have to leave it there. Okay, and checking the rise times and the fall times, I'm getting set up for the sawtooth now. My calibrator waveform was exactly a 50% duty cycle with an 8 I will double check now because I can't remember if it's micro or nano. It's exactly an 8.000 microsecond rise and fall time, so it is very symmetric and is looking good. This is just confirming that we have sawtooth out on A, and we have sawtooth out on B, and we have gate on B. As well as gate on A. And for the last step, it wants us to check the Graticule Illumination, but since we did the LED modification, we know the Graticule Illumination works just fine. Okay, for the trigger mode, I have the trigger selectors coming out of A20 and B20. Those come over here to the 7603, and they are both terminated into 50 ohms. Here's our ground reference setting, right in the center of the screen. So we'll flip these over to DC. And now, this is just checking the DC balance of the trigger selectors. So what I'm going to do is I'm going to hit right, left, and add on the 7904. And if everything is adjusted right, this line should not move. Here's left. That one's okay. Right, that's okay. And add, that's okay. So that's perfect. We don't need to mess with it. I had a slight error in that last check. It needs to be on vert mode A when we're checking. So recheck that here real quick. Everything's all set up. And it should move less than 1 division. That's left. That's add. That's right. It's fine. Okay, deviating slightly from the calibration document because I have available a 11A33 differential comparator. Using the 7A26 in inverting and adding mode to give it differential inputs in a 7603, which is what's called out by the calibration document, gives me about 75 to 90 megahertz of bandwidth. The 11A33 has 150 megahertz of bandwidth, so I'm getting better signal, or I'm getting more viewable signal, and it's a true differential comparator as opposed to using the invert, which has some error to it. I have it, so we're going to use it. Not necessary, but it's the best way to make this particular measurement during the calibration that I have in the lab. Also, the 7A33 can natively do 50 ohms. That's why there's no 50 ohm terminator. It is set to 50 ohms, so I have proper termination on the trigger lines. Here's our 6 divisions of display, and that looks very healthy. And that is with the signal standardizer installed. Okay, had to move back to the 7603 for this one because the way this waveform is built, this is what it looks like when it's zoomed in. This causes the DSA, the trigger and the digitizer and the DSA to have a hard to get very confused. So, but this is what we're looking for, and it wants 6 within the middle 6 divisions, so 3 up, 3 down. It wants the center 7 traces within 0.6 divisions. It's great, so no adjustment needed there either. Okay, I have to do the exact same thing for the B side, so I'm just going to do that off camera real quick and get through it because it's exactly the same process as the A side, just for the B slot. So no need to show it again. And as we can see, we're on B trigger, and B trigger gain is good. My signal out DC centering needs to be adjusted. It's a little high. It's within spec, or it's within test, but it wants to be right on the center line, because if I flip this to ground, that's where our center line is. So I'll move over to where that adjustment is. This particular adjustment is really confusing. It's on the left side of the scope. It's this potentiometer right here. And we have an adjusted signal out DC center. And for the thermal out, everything looks good, so I am not going to adjust anything there. Everything in that waveform looks healthy. Okay, the last step of the triggering section is fully populating the frame, 2 time bases, the signal standardizer, and an amplifier, and just checking all the trigger combinations, making sure the triggering is working the way it's supposed to. This one does, so everything passes, and we are good to go there. Next step is the horizontal system. Okay, here's the test setup for the limit centering, which is R630. After shorting test points 610 and 750, we should be within 0.5 divisions of the center line. We are, but it will need adjustment. Here's the shorting points. All right, up here's the horizontal board, down here's the vertical board. So the vertical board's the one that has more of the high-speed exotic stuff on it, because that's faster than the horizontal. So, but those are the 2 test points you short out next to the adjustment capacitors. R630, the limit center, is actually right here, and it just needs to be lined up on the vertical. And there it is. Okay, my adjustment for the horizontal amplifier centering is slightly off, but not bad. So I'm going to adjust that real quick. That is R121. R121 is right here on the horizontal board. Doesn't need much. Yep, still off. Okay, let me move the camera, I'll be back. And there we go, nice and centered. I do need to compromise that slightly for the B compartment. So we'll just touch that there. That'll probably put us back to where we were, but let's check A again. Yep, that looks good, and that's the best compromise between A and B, so we're good there. Now we are checking the vertical and linearity. I'm going to have to get square onto this one to check the alignment, but that looks pretty good right there, so let me just check it. Well, after getting the traces lined up, everything looks good, so the horizontal amplifier is just fine. I am starting to think this calibration has never been touched. Everything is in great shape. This is looking real good. Just some slight tweaks here and there, but this frame was in really nice shape. And the B bay looks good as well. Alright, getting set up to test the horizontal system. And we're checking the amplifier gain, which we look good using the signal standardizer. And we need to check the left compartment. This is what the signal standardizer is for, is to double check the gain of each compartment. So when you switch plugins, you don't have to recalibrate the entire scope. You can calibrate the scope with a set amount of plugins, but if you do that, you're locked to those plugins. As soon as you pop one out, it may not meet spec in the other port and vice versa. So that's really what this calibrator does, is it aligns the bays to each other. So you can move plugins around and still have an in-spec scope. And left side looks good. We need to change the rep rate to 1 kilohertz. And we need to make this a 2-division display. Now we're checking expansion and contraction. So we set it here. Turn up the Graticule Illumination so I can actually see it up top because it's in shadow. That is dead on. That's okay. That's all right. Dead on. Dead on. Dead on. And dead on. Yeah, so we have a little bit up top, but everything else is okay. That's good. Now I need my SG504, which we repaired in the last video. This is what it was for. Okay, here we go. Let's shoot for 4 points, or 5, above 500. Okay, I'm going to use my RF signal generator for this because I have the leveling. I have a level detector in the signal standardizer in my. So here we go at 6 megahertz. We have 6 divisions of display, and if I go to 550 megahertz, we have 4.6, so we're about 50 megahertz high, which is perfect. Let me move over to the other port, and we'll check bandwidth over there too. It's so close, I don't even need to check much matching. We'll do 550 again. And perfect. Looks like the left side's a little bit better, actually, in terms of speed, because I have a little bit more bandwidth over on the left, but we are good, and we have a nice clean sine wave. Everything looks great. Awesome. Okay, we're checking channel isolation. So I have signal going in. We hit over to the left. We have no deflection, which is perfect. This is a 500 megahertz signal. And let's check the left port. Which is good because I only have one 500 megahertz amplifier, so I almost couldn't do this part. Check the right side. No deflection. Perfect. We have better than 80 to 1 isolation on the channels, as expected. Okay, all the vertical modes work as expected. God, this thing is still shedding packing peanuts. What in the world? I hate packing peanuts. We're checking trace separation. So Alt. And chop. Trace separation is working just fine. And the next section for this is the readout system. But the readout system in this scope is working just fine, so it does not need any adjustments. Thanks for stopping by the lab and taking a look at this Tektronix 7904A. I have some more 7K plugins that I'm going to need to work on and get fixed. And I didn't have a frame that had been checked in because I know the 7854 is out of Cal. So this one's all checked out, so I can use this to repair some more 7000 series plugins. So there will be more of that to come, and I will see everybody in the next video.